guys, I'm here at IEEE. I'm here with PJ from Rose-Hulman Institute of Technology. Here they have a poster basically talking about their experience using the SpinQ. So can you tell us how did you guys, choose this machine? I guess why?
Yeah, so I wasn't involved directly with it, but I've talked a lot to the professor who was. Dr. Sai McCoon did a lot of research trying to find a machine that would be upfront friendly to new incoming students who had very little experience, and they wanted something they could easily get into and use. And so through his research, he found this machine that allowed a small number of qubits to be used, and you could directly see what gates were involved and how they could be implemented in ways to do different useful things in small quantities, so that you could get a basis for how quantum computing starts to work.
Nice. Are there any additions that you, like any extra stuff you wish they had or like came with it? Like, I guess, how would you improve this product?
Yeah. So I think the biggest thing that would be helpful is more kind of practice problems kind of built into the machine. The machine does have this Castor software that comes with a small number of like kind of homework style problems, but the problems are directly tied to the machine in the sense that you can only get the answers by directly putting them into the machine and then getting them. So more kind of practice style problems where you could kind of get the problems and the answers easily to give out to students so they don't have to be directly at the computer to kind of practice, I think would be really helpful.
Have you looked into their coming up devices?
Yeah.
Like I think it just kind of plugs into the computer directly. And
Yeah. So we did see they have some new computers that have more qubits and more software. So we are looking into maybe purchasing one or two of those to see what updates they've made.
Okay, cool. And I guess what kind of feedback have you gotten from the students about this project?
Yeah, so a lot of the feedback we've gotten was really positive. They really enjoyed being able to kind of hands-on experience what a quantum computer is. It's kind of one of those things that you kind of hear talked about, but you never really know what it is and what it looks like. And so they really enjoyed the practical components of this where they could see what a quantum computer was, and even if they couldn't do big 100-qubit calculations and stuff, they could get a sense of what a quantum computer really does.
Okay. Well, yeah, cool. Thank you. That's it for my questions, and thank you for your time.
Yeah, of course.
Hey guys, I'm here at IEEE Quantum Week. I'm here at the SpinQ booth. They got the fancy new quantum computer, and so I'm going to talk about it. So as you guys remember, last couple of years ago we did the SpinQ review for the Gemini Mini. We took it apart. Looks like it's back together on this one. But now they have it so that it's openable, and they like to show off all their parts. So that's cool. The first thing I noticed is that the resistors aren't there anymore, which makes me wonder if the magnets are better, or maybe they've figured out some way. The resistors I thought were to keep the whole thing at a certain temperature, but they don't seem to have those anymore. So just to give you guys a brief overview, we've got the FPGA board. Basically, computer connects here, and then the signals go out that way. We got the amplifier boards, and then we've got some power supplies and the electronics to control the shimming. Another thing that SpinQ's been branching into is the superconducting quantum computers. And so they've got this 5x5 2D lattice chip right here, and they actually have a sample right here, which is kind of cool. Have all the coaxial cable inputs, and I suppose that's the chip itself right there. So yeah, that's kind of cool. Here is their software. Basically, it's split up into theory and experiments, and they've got all sorts of experiments. Just like the last one, it has an auto calibration, and if you ever need any support, they have it so they can dial in and help you out, make things easier for you, all that stuff. I really like this openness of it too. Like you can see when operations are happening, the LEDs will turn on. Makes it very futuristic looking. One cool thing is every time you push buttons and stuff, the lights will change on the SpinQ. The other interesting thing is they've made it so that you've got screws, and you can actually remove the whole top and change the sample, which is a little scary to me because the 2-qubit is a dimethyl phosphide, which is a teratogenic and carcinogenic thing, but I suppose as long as you don't break the vial, everything's fine. Yeah, so you can also replace it with water if you only want to do 1 qubit operations, spin, stuff like that. Yeah. So on their website, on their Hey guys, I'm here with Dustin at Penn State. He is talking about his research on flux noise, and it's a bit above my pay grade. I kind of get the spectrometer and quantum devices, electron paramagnetic resonance, but let's ask some questions. So Dustin, what is flux noise?
Yeah, so flux noise is noise that's created by paramagnetic spins. These paramagnetic spins tend to lie on the surface of our qubits, right? So that is creating all of the decoherence, which is currently affecting our ability to scale up quantum computers to have more qubits and really enable quantum computers to thrive. So that's flux noise.
How did you detect it? Like, how does that machine work?
Yeah, so what we're using is EPR, electron paramagnetic resonance. And so electron paramagnetic resonance is very popular for detecting paramagnetic spins, right? So these spins that are causing the flux noise. But typical state-of-the-art, like the commercial state-of-the-art, can only detect about 10 to the 10 spins in a sample. But with our method, what we do is instead of using a cavity, microwave cavity, to send our microwaves in, and then what happens is the microwaves are absorbed by the paramagnetic spins, and then they flip spin, which then causes a change in the power of the microwaves in the cavity, and then we detect that change in the microwave power. But instead of using a cavity, what we've done is use a small non-resonant probe. And the small non-resonant probe loses all of its what we call quality factor, which is the amount of energy stored over the average power that is dissipated. But what we get instead with the small probe is a major increase in filling factor greater than the loss of our quality factor. And the filling factor is essentially the amount of microwave energy that our probe creates that ends up stored in the sample. And so by using that trade-off there, then we actually get an increase in sensitivity over standard EPR using a cavity. And then from there, we did an experiment to see, so then what is our sensitivity? And so we put DPPH on the surface of a silicon wafer, and then we just compared, we put it in a commercial state-of-the-art spectrometer.
Sorry, quick question. What's DPPH?
Yeah, DPPH, I don't know the full name, it's like diphenyl something.
But basically it messes with the spin?
Yeah, so it has a bunch of paramagnetic spins.
Okay.
It's I think it's more of an organic compound, which is actually commonly used in EPR as a spin.
Oh, okay, yeah. I think I've heard Zeke talking about it before.
Yeah. It's less popular nowadays, but there's plenty of things you can use, and DPPH is still really popular. So that's exactly what we did. We just diluted the DPPH and then put it on top of our silicon wafer, so we end up with a really thin layer of it. And then so we put it in a commercial spectrometer, and then we were able to count the number of spins, and then we used our probe and compared the number of spins that our probe sees, essentially, right? And so I have the calculation here. I'm not going to go through all of it, but you do the calculation, and we see that we can actually detect 8.9 times 10 to the 6 spins using our probe. And like I said, the standard state-of-the-art requires 10 to the 10 spins. So we're essentially 10,000 times more sensitive than state-of-the-art.
Wow.
And so if you look at papers that talk about how many spins are actually on the surface of like a small qubit sample, it's much smaller than 10 to the 10, but we believe around 10 to the 6 will actually be able to pick up signals on the surface spins. And if we can do that, then we can tell you what the defect is, and then once you know what the defect is, it's a lot easier to figure out, okay, how do we get rid of that defect, right? So that's the idea. So we don't yet have any qubits to actually test, but that's essentially the next step, is to get a qubit and get a signal. So
that sounds great. This has been Dustin from Penn State. Thanks for taking the time to talk to us.
Yeah, thank you.
Cool.